Alrighty.
Great.
So good afternoon, everyone. And thank you for attending day 3 of the Watershed Summit and Innovation Contest. I am Ginger Goldsberry. I'm the treasurer of the Friends of Lake Warner, and I'm thrilled to be here, and I'm thrilled to have you here. So let's begin with Dr. Ljiljana Rajic. Yes.
Well, good afternoon, everyone. I'm very glad that you invited me to give a short presentation on Elateq and what we've been up to for this past couple of years. My name is Rajic, and I'm a Chief Science Officer and the co-founder of Elateq. Elateq is an Amherst-based water treatment company. We are located actually at the Institute for Applied Life Sciences at UMass. That's where we have our laboratories. Prior to founding Elateq, my entire career was in academia. I was a researcher for almost 15 years, doing research primarily in environmental science, environmental electrochemical treatment systems for soil and water treatment. And just before I established Elateq and founded Elateq with my partner, I spent nearly 6 years at Northeastern University, where I led green remediation laboratories at Civil Environmental Engineering Department, where we focused on groundwater treatment, electrochemical water treatment, and that was funded by National Institute of Environmental Health Sciences, a really wonderful project that looked into different impacts of contamination and mitigation of exposure to contaminants.
I apologize.
Okay, we're back.
That was an errant click. I didn't mean to do that. So there's going to be 2 recordings. I apologize.
Oh, no worries, no worries. Before I dig into talking a little more about the technology itself and some of the studies we did so far that are relevant for this group here, I would like to introduce our team. Beside myself, Rod Anderson is a co-founder and a CEO of Elateq. Linda Rauch is our interim Chief Technology Officer and also engineering practice leader at Nextron Technology. Aidan Berry, who's our Chief Development Officer and actually a graduate out of UMass, and Nick DiCaprio, our electrical engineer. Throughout the course of our product development, we have an array of partners that helped us in different capacities and still helping us that you can see below, and we are always grateful for them. I'll just dig in right away to the technology itself since we don't have much time. Our technology is electrochemically based, meaning that we don't use any chemicals, adding any chemicals into our system, either for operation or maintenance. It is all-in-one treatment, meaning that we can remove a range of contaminants at the same time throughout our system. And since it's all electrochemically based, all the monitoring and control of operation maintenance is done through a range of different electrical devices. So we can say that it's a fairly easy plug-and-play operation of our system. Often people think because this is electrochemical technology that it uses a lot of electricity simply because of the name and the concept, but it's actually low energy consumption, especially comparing to some of the commercially used now technologies with similar properties of that all-in-one treatment approach. Our technology so far has been focused on polishing the wastewater for industrial municipal wastewater treatment, as well as groundwater application. The core of our technology, as I mentioned, is electrochemically based, and it's actually the innovation behind it and the uniqueness is that it merges different concepts of electrochemistry. I'll just mention a few. It's use of 3-dimensional electrodes. In our case, that's our proprietary carbon material. It uses bipolar electrochemistry, which is a concept that is used in some systems separately, as, for example, electrocoagulation flotation systems, and conventional electrochemistry used in other applications. So this is something that we managed to merge together to create this powerful technology that can remove a range of contaminants at the same time. Just an example, if we talk about organic pollutants, our system degrades them or transforms them to harmless byproducts. Whereas when we talk about metals, since we cannot degrade elements further, metals are actually securely stored within our electrodes. And upon saturation, these electrodes actually become a valuable resource for one of our partner companies that are extracting metals from different solid media. So this is just to give you a sense that we are really, as we are looking on our technology and applications, we are really taking this sustainable approach to close the loop when it comes to waste, when it comes to energy use, and really be on this water energy nexus field as much as we can with the novel technology. Since Elateq was founded, we actually incorporated last year in March, but we established Elateq in 2019. We were awardees of a couple of Massachusetts Clean Energy Center awards, simply as they recognize that our technology is in this water energy nexus. And I'll talk more a little bit about this Innovate Mass project, which is actually a local project to Amherst and of, I think, relevance for this group. As I move forward, I structured this as to introduce our technology in terms of applying it in two different configurations. One is as a flow reactor, excuse me, as you can see here in these photos, and the other one is something called permeable reactive barrier configuration, which is more applicable for mitigating non-point pollution sources, and I think that's relevant to mention here. And I'll talk a little bit more about that as we move forward. So when it comes to plug flow configuration, that means that we use pumps to pump the water through our system. Contaminants get removed, degraded, and then the clean water comes out of the reactor. And this configuration has been so far used in different piloting, lab scale, and demonstration for range of really wide range of wastewater. Our very first pilot was at the South Hadley wastewater treatment plant that was funded by Massachusetts Clean Energy Center, where we introduced the 3,000 gallons a day capacity pilot system with the goal to remove E. coli and lower the amount of nutrients in the secondary wastewater, which we successfully achieved over the course of 5 or actually 6 months of the piloting phase. Further, what I also thought it might be of interest here is the demonstration of our unit at metal plating or finishing facility. So this is industrial application of our plug flow configuration, where even though the facility had their own wastewater treatment, the majority of metals, especially chromium, zinc, and nickel, were still above the permitting levels at the facility. So our system achieved these permitting levels, and below that during the course of 6 months of our demonstration at this facility. But also in addition to that, we managed to lower BOD levels as well as nitrate that were of concern at this facility prior to discharge in the water body. And this one is actually also interesting. It's a lab scale testing that we conducted, but it was done for a company that introduces treatment trains for treatment of our agricultural wastewater. These results are related to dairy and chicken farm wastewater. So our system was tested as an addition to their current treatment train, where we managed to achieve the desired levels of BOD, COD, and some of the nutrients that they needed to lower prior to finalizing their treatment system as well. So these are all plug flow, as I mentioned, those are more applicable for point sources, but when we talk about non-point sources, they're a little bit more difficult to address, and the permeable reactive barriers are often used, PRBs are often used for capturing plumes in groundwater. So some of these non-point sources can be mitigated this way. And the principle is that the PRB is constructed and installed permeable to the water flow. The water flows through the whatever reactive media is, depending on the contamination, and then the clean water is leaving the barrier as it flows through. So in that sense, our current project with the town and the project that is supported also by Massachusetts Clean Energy Center is one of the local areas where the drainage from house footing drains and yard drains has elevated concentrations of iron, and because of that, the water cannot be released into the water body, and it has to be handled by the town wastewater treatment plant. Some of the limitations that limits which technology can be used for this type of treatment are that there is no power access at the site. There is a limited footprint for solar panels. So even if you were to install, for example, pump and treat system, you still need a lot of solar panels to provide enough power for the pumps required for pump and treat. And also another challenge is that there's a lot of variable water flow due to seasonal changes, right? So this location required a different solution than to what pump and treat systems would allow. So we redesigned and refined our reactor designs that can be installed in the manhole where the water, all that drainage water is focused to, in order to allow as the water flow through this reactive barrier, iron is removed and the water is the concentration of iron is less than 1 milligram per liter and can be then released in the into the water body. So this entire system is going to be solar powered. So we are now in the midst of finalizing the assemblies and starting the installation. And this installation is actually because we are installing our low energy use system, comparing to pump and treat. Even if the pump and treat was to include the Elateq flow configuration, would be significantly less use of energy than any other alternatives. And we estimate that nearly 100 tons of carbon dioxide will not be released into the environment because of use of our system. That's over a 30-year estimation. But significant energy savings, and the limitations of this site are managed by our design. I just wanted to, I believe this is a great moment to just introduce quickly our next steps and invite anyone who sees this as an opportunity to collaborate with us on our next steps, as we are fine-tuning our technology and system design for municipal wastewater reuse and for non-point contamination source mitigation, where we want to really dig into more understanding primary mechanisms for nutrients removal and how we can enhance our systems, because there is a lot of room there for encasement of nutrients removal that now we are focused to do so. And if you know, anybody sees this as an opportunity to work together for specific sites as either piloting or research, I'm open to further discussions. And with that, I want to really thank you for the opportunity, and I'm open to any questions, and you can either send them directly to me at this email address here or through the organizers. I'm okay with either way. And again, thank you so much.
Thank you, Ljiljana. Does anyone have any questions?
Allison's got her hand up.
Hello, that was a fascinating presentation, and very exciting. So, as most of you know, tomorrow I'm going to be talking about cyanobacteria. And the reason is because of the concern of cyanobacteria toxins, which are approximately amino acid size molecules. And my understanding is that they are not currently treated by the routine water treatment options in our drinking water systems. And I'm just wondering if your technology would be adaptable to that type of contaminant, organic pollutant removal. And my question is, does each of your plug flow reactors need to have a specific protocol addressing whatever it is that is being targeted, or is it a very general removal system?
Oh, thank you, Allison, for those questions. Yeah, we haven't done any testing for those specific toxins, but that's definitely something interesting we can look into. And in terms of your second question about our reactors, they are not specific for, you know, it's all in one treatment, so we don't target certain contaminants with our units. So the setups are general for the wide range of contaminants. There are certain tweaks that if the water is primarily very high organic load, where we need to really induce a lot of oxidative species in the system, we can fine tune some of those reactions and rates, but it's fairly general in terms of the structure of the units. I hope that answered your question.
Thank you.
Thank you, Allison. Michelle?
Can you remove phosphorus? Because in that list, I see phosphorus among nutrients. You had nitrogen.
Yeah, so we have data on when we did the testing for municipal wastewater, as well as some of the agricultural, the phosphates, we can remove phosphates to approximately 50%, and we didn't achieve more than that. So that's why we are now looking into digging more deeply into the mechanisms that we can better support those specific removals of phosphates as well as nitrates that have been more challenging.
Terry?
Thank you.
Thank you.
And I have a question. I'm at UMass, and we do have reclaimed water. So I saw that you are using this technology for reuse. I think the town of Amherst and us would be interested in talking with you and the technology, as well as when it goes through your system, how does it compare for cleanliness for going through an RO system? Because we use it for boiler water makeup as well as for cooling towers, and we're looking to get more capacity.
Yeah, that would be great if we can talk more about that. We do compare to reverse osmosis in terms of the water quality. So that would be definitely something we can talk in more detail about. We actually did our one other pilot testing we did at Vet Center with Professor Dave Rakow at
Okay.
Yep. Yeah. So that would be great.
I just put my email into the chat, and we can try to chat after the presentation. So thank you very much.
Thank you. That's great. Thanks.
Well, thank you for everyone for your questions. Thank you, Ljiljana, for your presentation. And Matt, can you send yours through chat since we need to keep moving?